So in the example from page 169, we're using the same equation with the trucks and the price value versus the miles driven. And what we're going to do here is we're going to find the residual for this example, then we're going to interpret it. So a truck that has 70,583 miles driven and a price of $21,994. We're going to find the residual for that and interpret what it means. So we went ahead and plugged in the mileage in for that variable into the least square regression line equation. And we got a predicted price of $26,759, which is clearly above this one. Let's actually go through and find the residual now. So the residual is going to be your actual versus your predicted, or sorry, not versus, your actual subtract your predicted, so 21,994 minus 26,759, and your residual ends up being in dollars negative $4,765. So the interpretation is the actual price is $4,765 lower than expected, based on mileage. Now the interpretation should include the based on mileage because in this example alone, there are many other factors besides mileage that go into a car's value. But just in this case, those are the two variables, your explanatory and your response. So to find your residual, plug in your x into the equation, calculate your y, and then subtract your predicted y value from your actual y value. It could be positive or negative depending on the situation. If it is a negative residual, like here, that means that your predicted is lower. Sorry, your predicted value is higher than your actual value. And if it's positive, it's the exact opposite. All right, least squares regression line. We talked a little about this before, but a least squares regression line takes all the residuals, squares them, and then sums them up. And what you get there is some sum. So any human could do that. They could make any line they want, find the residuals, each of the vertical distances here, like for example right here, and then add them all up and square them, add them all up, and you get some sum. But what the computer does for you is it does that, and it finds the line that has the smallest sum. So you'll see this is the line, these are all the squares, and here's the sum of the square residuals. Now that number is not meaningful out of context, but it's important in the fact that that is the lowest sum for any possible regression line. So the computer went ahead and found the lowest sum, and it made it the regression line that it is. So why square the residuals? Well, just like with standard deviation, and we had to square the deviations, if you find all the residuals for every single point here, they cancel out to 0. So that's why we square the residuals. So if you were to sum the residuals, you would get 0. This is why we square them. So that's why you have these squares popping up on your graph there. We're squaring the numbers, and that way you have all positive squared residuals. So the computer or computer software calculator finds the smallest sum. And that's where we get the least squared, least squares regression line. That's where the name comes from. The least being the minimization of the sum, squares because we square the residuals, and regression line is because it's a regression line. Now we're going to run through real quick how to use it on a TI-83 or 84. Some of the newer models have different software. It may look a little bit different than what my older TI-83 Plus looks like, but it does the same exact calculations. So you're going to be able to determine the equation of a least squares regression line using technology or computer output. So how to use a calculator to produce a least squares regression line. You're going to use the data from page 172. That is the SEC football points per game versus the number of wins for the entire season. So if you go into stat, you go to edit, you type X into L1, Y into L2, and if you want to do a scatter plot, go to stat plot, turn it on. It's the first option, and let's make sure that the Y variable or Y list is going to be, oops, hold on, L2, there we go. All right, so we're going to graph this, zoom 9. That's what our data plot looks like. So if I'm just going to sketch it real quick, it looks something like this. And this is points per game, and this is wins. Now if you want the least squares regression line graph with it, go back to stat, and we're actually going to do the calculation for it. It's option 8. We're not going to use AX plus B. We're going to scroll down to A plus BX, which is option 8 right here. So click that. Now, if you want to store it into Y1, you have to, in this old calculator, go to vars for variables, Y variables, function, Y1, and it'll store it into Y1 for us. So this equation, instead of copying these numbers into Y1, it already does it for us. We get our R squared, then A and B. A is going to be your y-intercept, B is going to be your slope. If you click on Y equals, you'll see it pop up right there in the equation bar. So if you graph this alongside of it, you'll see the least squares regression line kind of go right through it. So looks something like this. Okay. If we go back to the equation, something like, we'll say negative 3.75 plus 0.44x. Okay. So, what if we want to predict x from y? So we've already done the predict y from x. What if I want to do the reverse? What if I want to give you a y and then predict the x? You'll notice that because the residuals are vertical, if you were to plug in a y and then solve for x, you get the wrong prediction because the residuals are vertical, not horizontal. So if you swap the variables around, it gives you a different equation actually. So if you were to take this regression and do L2 then L1, so L2 would be your x and L1 would be your y, you get a different equation entirely, and therefore you have to, if you're going to predict a x from a y, you need to swap L2 and L1. The reason why is because residuals are vertical distances, and because they're vertical distances, the least square regression line relies on those vertical distances. If there was somehow measuring both directions, vertical and horizontal, it'd be different, but the fact that they're only measuring vertical, you have to switch them around. So we do this because the least square regression line is computed by minimizing the vertical distances from the observed y values. If we change x and y, that same line has minimized the horizontal distances. And that's not what a residual is. So we don't want, in order to avoid that, we swap around, we recalculate by switching the variables. Some facts about residuals. A residual will have a negative value if the observed value falls below the regression line. The regression line overestimated the value. A residual will have a positive value if the observed value falls above the regression line. We call this underestimating, or the regression line underestimated the value. The sum of the least squares is always as small as possible. That's why it's called least squares regression line. It's always as small as possible. So we try and use least squares regression line to help us predict things that are happening in a linear relationship, but sometimes it's hard to tell from a scatter plot if it's actually linear. So we use what's called a residual plot that helps us determine if the data looks a little curved. It's easier to tell because you take your line and essentially, if it's like this, the graph's going to make it horizontal, and you'll be able to see there's a curvature around the line itself. So residual plots. It's a type of scatter plot in your calculator. It plots the residuals against the explanatory variable. So whether the residual is positive or negative, it appears above or below the line of 0. It's used to determine whether the least squares regression line is an appropriate model for the data. The appropriateness becomes from is it curved or is it linear. It is usually easier to see something unusual with the scatter plot when the regression line is horizontal. It just makes a little more sense. When you're looking at it like this, it's sometimes hard to tell if it's curved. But when you take it and you just turn it like that with the residuals, it becomes a little bit easier to look at. So, making a residual plot in your calculator. Keep explanatory response in L1, L2. You're going to calculate regression line first. You have to do this first. The calculator doesn't know otherwise. It'll come with an error. So, same thing, calc in the stat menu. Press enter. We get our equation. Now, if you want to go ahead and, I'll clear out Y1 real quick. If you want to go ahead and make a stat plot with a residual plot, turn on the plot 1. You're going to keep scatter plot option highlighted. But the difference here is the Y list is not going to be L2. You're going to change this, and it looks different on different calculators, but in order to change this, you're going to press the list button, and you're going to click the RESID, that stands for residuals. So the calculator actually goes through and do all the residuals for you, no work whatsoever, and it takes them and it graphs the residual plot. So I'll zoom 9. And you'll notice we have a horizontal line representing our least squares regression line, and we have data surrounding it. So we got a positive residual here, negative, slightly negative, negative, positive, positive. And from the residual plot, you can't tell any curvature there. So this is okay. From this point, you can say, after looking at the residual plot, we're good with looking or using a least squares regression line because the data is not curved at all. So to sketch it, it's going to look something like this. You need to draw your horizontal line, sketch your data around it just like that, and that'll be your residual plot sketch. Now, patterns to look for. I have 3 examples on the notes here. First, no pattern. So points are scattered above and below. And this means it's appropriate to use that least squares regression line. So both above and below. So the least square regression line is appropriate. All right. This is a pretty drastic curve here, and it might be somewhat obvious on a regular scatter plot, but sometimes it's hard to tell. So here, this would be a situation where you have a curved residual plot, so a curve pattern. So the least square regression line is not a good fit. And then here, fan shape pattern. So one area of the scatter plot is pretty accurate, and then once you go past a certain point of your explanatory variable, it becomes less accurate. So you can still use your least square regression line. It's appropriate, so is appropriate. just take precautions. Especially when you're predicting down here, it's less accurate as a model. Okay. So just look out for those things when you're doing a residual plot. Keep track of when it's appropriate and not appropriate to use least square regression lines. All right. So you're going to be able to interpret now the standard deviation of residuals and R squared and use these values to assess how well the least square regression line models the relationship between two variables. So you can make a model. Anybody can use your calculator to type that in and get an actual equation. But the question is, how well does it actually fit the data? Is it appropriate to use besides just looking at residual plot? How accurate can I actually be? So the standard deviation of the residuals gives you the typical prediction error, or the residual, sorry, of an actual prediction. So the equation for this is S equals the square root of, you're going to sum the residuals, or you are not, but the computer is, squared divided by n minus 2. Now the n minus 2, you're thinking of let's say average or mean of something, you divide by n. The n minus 2, we'll get into why it's minus 2 in the coming chapters. Right now we're going to just stick with this is the average error, and you see that by having the denominator being divided by the number of actual residuals. This also, if you write it out the full mathematical way, so y minus y hat squared divided by n minus 2. You notice it looks very similar to a standard deviation of just a data set, except it's n minus 2 instead of n minus 1. And that's what we're looking at here. So just to remind you what this looks like. Very similar to the standard deviation of an actual univariate data set. So if it gives you if you find a standard deviation of the residuals, you can kind of say, well, this is my prediction error. I could be as far off by this many thousands of dollars or hundreds of dollars, whatever the variable is. So if you flip this over, you can also look at the coefficient of determination, or R squared. That is your correlation coefficient squared, R squared. It is the fraction of the variability in the values of y that is explained by the least squares regression line of y and x. The higher, the better. This is only when you have a linear relationship. You can only use this for a linear relationship. Sometimes R squared values are very high for nonlinear relationships, but students or people still tend to use them, and it's really inappropriate to actually use them. Range of 0 to 1, because we know that if you're squaring a negative number, it becomes positive. So if R is in between 1 and negative 1, that means R squared is going to be between 0 and 1. If I square a negative 1, guess what? It becomes 1. It'd be on this side of the range of possible values. Squaring 0 obviously gets you 0. Anything in between, if you were to square 0.5, 0.5 would be 0.5 squared would be 0.25. That lands right in here as well. Obviously, the higher the number, the more accurate the relation or the model can be. The equation for this: R squared equals 1 minus sum of the residuals squared, those appear again, divided by the sum of the response variable minus the mean squared. So for example, if R squared is 0.89, then you would say the following: 89% of the variability, or don't say variations, they say 89% of the variability is accounted for by the least square regression line. So, comments on the equations for both coefficient determination and then the standard deviation of the residuals. You'll notice that they both have a sum of the residuals squared. and they both describe how well the line fits the data. So you use these two numbers in tandem to actually help you just determine how well is that line actually fitting with the data. So S does it with units. S will actually have units to it. R squared has no units. So this does it without units. So if you were to change from inches to feet, that number does not change. This number will change though if you were to change units, as far as inches to feet, dollars to cents, whatever it may be. If you're looking for an example for standard deviation of the residuals, back to the truck example with the mileage, I do believe in the book it was something like the standard deviation of the residuals was like $4,000, which means that your predictions can be as far off as $4,000. So that prediction of $26,000 back in this example, the very beginning of the video, here, this example here, our prediction residual was off by $4,765. The actual residual being that far, or the residual being that number, and our number or standard deviation of residuals being that close, tells us that we were probably could be within the realm of possibility with that line. We also could be $4,000 off the other direction as well. But it gives you an idea how well you can actually predict with. It gives you a range of possible values. So you're going to use these two numbers to determine how well a line fits. If your R squared value is 0.05, then you can tell right away that your least square regression line is not that good a fit for the data. And maybe it's not linear at all. Maybe it's a nonlinear model, or maybe there's just no association whatsoever. So keep that in mind when you're looking at least square regression line if you want to determine whether or not it's appropriate to use that equation.